Hello to all physics enthusiasts and fans of physical experiments. This is Andrei Shetnikov with you, and today we're going to discuss an interesting question that was asked by our subscriber, Maxim Kovalev from Khabarovsk. And the question is as follows. Let's say we have rafters that rest on the walls. But if snow falls on the roof, it's clear that these rafters transfer that load to the walls, including in a way that starts to push them apart. And the question arises, is it true that when a fixing beam is inserted between the rafters in this way, the thrust load on the walls only increases because of this and does not decrease, although this seems paradoxical at first glance? So first we'll discuss a simple school problem about rafters, and then we'll move on to this more complex one. And here I have these rafters that are hinged together at the ridge. I'm setting them up and hanging a weight on the ridge. And I'm asking what additional force caused by this weight is now pushing the walls apart. I'll first solve this problem theoretically, and then we'll check the result in the experiment. And I'm asking what additional force caused by this weight is now pushing the walls apart. So, I'll first solve this problem theoretically, and then we'll check the result in the experiment. And the force applied to the ridge, which we can conveniently denote as 2F, so that each half has a force F, and this will be the force of the vertical reaction of the support. And we need to find the horizontal reaction. There's the force with which the beam pushes against the wall, and there's the force with which the wall pushes against the beam. So I've labeled this force here as N. Well, for equilibrium, it's clear that the second beam must push with the same force N in the opposite direction. And right now, all my forces are balanced, but we also need to balance the moments of these forces. Well, the force F acts on arm A, its moment is Fa, and the force N rotates in the opposite direction, applied to arm H. Its moment is Nh, so we have the moment equation, and from here we find N, which is F multiplied by A divided by H. Well, in the setup I showed you, the height H was 16 centimeters, and 25 centimeters is half the span between the walls. Well, when we divide one by the other, we get 1.56 F. And now we'll check this in the experiment. And now the beam is resting on the force sensor at one end, and there's also an important addition. Underneath it, there's a smooth metal plate so that the beam doesn't dig into the wooden support beneath it. And all the force is applied to the sensor. Well, here I have a weight of 2 kilos, so each half will have 1 kilo. As for the pushing force, the theory predicted a coefficient of 1.56, which means 1.56 kilograms of force pushing outward on each side. Well, let's convert it to newtons, and we need to multiply by 9.8, which gives us 15.3 newtons. Now I'm taking the weight, 15.3 newtons. Now I'm taking the weight. Now I'm taking the weight. By hanging it up, we see excellent agreement between theory and experiment, well within the margin of error, of course. And if snow falls on the roof, then we must now apply the force acting on each slope to the middle of the beam. Well, accordingly, the arm of this force will decrease by half. Instead of A, it will become ta in half. And in our formula, we will have a 2 here in the denominator. And I should also mention that when H is small compared to A, this fraction becomes quite large. And the pushing force can become much greater than the force pressing down on the roof from above. And this is all very similar to the situation discussed in our video called Rope Machine. I highly recommend you watch it. And now let's add a beam to the rafters. And from a simple school problem, this task becomes quite complex. It's statically indeterminate, and such matters are discussed in the course on strength of materials. But I won't write any equations right now. Instead, I'll share some simple qualitative thoughts with you. So, I made this truss model out of thick cardboard strips so they would bend well during the experiment. And look, when there's some load on the trusses, their midpoints not only go down when they bend, but they also come a bit closer together towards the axis of the system. And when we insert a beam between the trusses, it prevents those points from coming together, which creates additional thrust that gets transferred to the walls. Now, I'm going to do a live physics experiment, starting with the trusses without the beam. And when we insert a beam between the rafters, it does not allow these points to converge, and therefore creates additional thrust, which is transmitted to the walls. Now I'm going to do a live physics experiment, starting with the trusses without the beam. The load on the entire roof will be 110 N. We're starting the experiment, the trusses are bending, and we're waiting for the vibrations to settle down. And here, the vertical load on each support is 55 N, while the thrust load is 68 N, according to the calculations from the first part of our video. Now let's do the same experiment, but with the beam. The vertical load on each support, as expected, is again 55 N. And the thrust force increased from 68 to 105 N, which is more than 1.5 times. 10 N. More than 1.5 times greater? More than 1.5 times. Now I'm going to do an experiment with these thin trusses and the beam on our testing stand. And I'm resetting the sensor beforehand, just like we did in the first experiment, so that it only records the thrust load that will be created by the weights. The setup is shaking, and the sensor readings are also fluctuating near zero. And now I'm hanging weights, each weighing 20 grams, at the midpoints of the trusses. And the sensor reading for the thrust created by the weights is just over 32 grams of force, which is a significant measurement in this context. Now, moving on to the key experiment, I'm carefully cutting the beam to observe the effects and gather more data. And the readings dropped to 22 grams. And so, not only in live physics, but also in the real experiment, we found that the thrust with the beam is 1.5 times greater than the thrust without the beam, no matter how paradoxical that may seem.
It's always heartwarming to see the theory and experiment agree. But the question arises, why didn't Andre use the setup he showed at the beginning of this video for the experiment? Let's conduct an experiment with it. First, let's do the experiment without the beam. I'm resetting the sensor and hanging 1 kilogram weights on the trusses. And we see that the thrust load on the walls is 700 grams of force. And now let's do the same experiment, but this time with the beam. I'm resetting the sensor, hanging the weights, and we see that the thrust force has decreased to 330 grams. And so, on this setup, which looks much more like real trusses with a beam, we found not an increase in the thrust force by 1.5 times, as in Andre's experiment, but a decrease in that force by more than 2 times. So what's the deal here? So what should builders rely on in practice? That's the question. So we invite you to answer this question and share your thoughts in the comments below this video. And now, thank you for your attention.